In mathematics, certain things are absolutely true. When we state that 2 plus 2 equals 4, we aren't estimating. We know it with absolute certainty because we defined the rules from the ground up. Look at this animated diagram comparing a perfect mathematical shape to a physical one. The circle on the left is governed by a precise equation. Every single point on that line is the exact same distance from the center. But on the right, if you zoom in on a circle drawn on paper, you see microscopic jagged edges of graphite and uneven wood fibers. The mathematical equation describes an idealized object, a perfectly thin boundary floating in an exact, featureless space. Those perfect geometries do not actually exist anywhere in the physical universe. Because of this limitation, the pure certainty we find in a mathematical system is an entirely different thing than the physical certainty we can achieve in the real world. This photograph shows Albert Einstein, who noticed a deep tension in this relationship. He pointed out that as mathematical laws become more strictly certain, they actually move further away from describing our messy physical reality. We naturally struggle to understand this gap because human brains tend to confuse the representation of a thing for the thing itself. This is a historical map of India. It accurately outlines the geographic borders and the major topography of the region, but it completely ignores the sounds of the cities, the shifting weather systems, the daily traffic, and the physical smell of the monsoon. Mathematical equations and physics operate the exact same way. They are extraordinarily accurate representations of reality, but they are not the physical reality itself. When you take a perfectly precise mathematical law, like the equation for gravity, and apply it to a physical falling object, you immediately introduce uncertainty. The law works perfectly only if you ignore the atmosphere, the wind, and minor measurement errors. This diagram illustrates how science actually works by moving through 3 distinct layers: reality at the base, the model in the middle, and mathematics at the very top. Take a look at this physical pendulum swinging back and forth. A heavy, uneven weight pulls on a frayed rope. The ambient air slows it down, and friction at the top pivot point constantly drains its kinetic energy. To study this motion, scientists build a model. We intentionally strip away physical complexity, erasing air resistance, ignoring friction, and pretending the rope has zero mass. We move up the ladder until physical properties vanish, leaving only a pure mathematical equation representing ideal oscillation. We discover the underlying structure of reality by deliberately ignoring almost everything about it. Pure mathematics derives its truths strictly from internal definitions and logical axioms. Science works backward, checking its structural models against physical observation. For thousands of years, scientists assumed that the rigid, flat rules of Euclidean geometry perfectly matched the actual physical space of the universe. Look at this flat grid. If you draw 2 parallel lines here, they never touch. But mathematicians invented totally new geometries where space itself curves. If you draw those same parallel lines on a warped spherical surface, they will eventually intersect. This is a photograph of Earth from space. When Einstein began calculating the physics of gravity, he realized that the physical universe actually utilizes this non-Euclidean geometry. Massive planets physically curve the space-time around them. Pure mathematics creates the structural possibilities in the abstract. It takes empirical observation to determine which of those possibilities nature actually uses. This gap between abstraction and reality is why learning advanced mathematics often feels incredibly difficult. When confronted with a complex calculus equation, it is easy to fall into the trap of treating it merely as a collection of symbols to be rearranged until you find the answer, without ever asking what the variables actually stand for. There is a strict difference between computational difficulty, which is simply not knowing the mechanical steps to integrate a mathematical function, and conceptual difficulty, which is not knowing what a derivative represents in the physical world. Advanced math causes friction because your brain is attempting to process the real-world physical object, the abstract structural model, and the dense mathematical notation all at once, usually without a clear mental bridge. The solution to this conceptual confusion is a specific learning sequence called the 3-pass method. In Pass 1, completely ignore the math and observe the physical reality. A heavy car is rapidly speeding up down a straight road. In Pass 2, you build an intuition. You translate that physical action into a measurable concept, asking exactly how quickly that vehicle's velocity is changing from second to second. This diagram shows the third and final pass. Only after you grasp the physical action and build the intuition do you assign the formal mathematical symbols, representing how velocity changes over time to arrive at the derivative for acceleration. Genuine mathematical understanding is not the memorization of abstract rules. It is the fluency to comfortably translate backward and forward between a perfect mathematical structure and the messy physical reality it tries to describe.